So we've talked about how work is measured in a unit of energy, joules. And it turns out we can connect work to what's called kinetic energy, or the energy associated with motion. So kinetic energy, K, is given by 1/2 mv squared. That's our definition of kinetic energy. So 1/2 mass times the velocity squared. Let's make sure those units make sense. So the units of kinetic energy should be joules, but this would be kilograms, meters squared per second squared. And if you remember, and you may not, but our joules, which was a force times a displacement, so it was a Newton times a meter, which putting in for Newton gave us kilogram meters per second squared, then times this second squared. This is, in fact, the same unit. So the units work out for our kinetic energy. And then there's a theorem that's called the work energy theorem. And it says that the work total, or net total, I kind of like total better, but either way works, is equal to the change in kinetic energy of an object. So let's see how this shows up. So if, for example, we take an object and we release it from some height, it's going to fall down. So its displacement is going to be down, and the one force, if we neglect air resistance, the one force that's acting on it is going to be our weight, mg. That's the force. Right? So the work that's done, the work done by the weight is equal to the force, mg, times the displacement. They're both in the same direction, so everything works out. I don't even have to do a dot product because the angle between them is 0 and cosine of 0 is 1. So that's the work done. If it's starting from rest, then the K initial is equal to 0. So we get mgd is equal to 1/2 mv final squared. And there we go. Now, this is our final speed right before it hits the ground, right? If it hits the ground and then stops, as it does, then we would say, hey, after it hits the ground, then the final speed is equal to 0. So our change in kinetic energy final minus kinetic energy initial, it went from 0 at rest to being at rest once it's hit the ground, so that would be 0. So our total work would be the work done by the weight, the work done by gravity, plus the work done by the ground to slow it and stop it. And though that must be equal to 0. So that says that the work done by the weight, which is this mg times d, must be equal to negative the work done by the ground. In other words, the ground provides, once it hits the ground provides a normal force up that opposes that's in the direction opposite from displacement, so that is a negative value. And it turns out that it's just equal to whatever this number is. We don't necessarily know the force of the ground. It's going to be changing and depends on how springy the ground is, right? I mean, it is a normal force, but that normal force is going to adjust as this comes flying in and impacting, and it'll happen over a fairly short period of time. So that's how this work energy theorem shows up. Now, where does the work energy theorem come from? We start with this equation and we do a little bit of calculus. We say, hey, the work from initial to final is equal to F dot dr, but we know force is equal to mass times acceleration, right? The sum of the forces. And so if this is my total force, then this is going to be my total acceleration, my net acceleration. So work is equal to, from initial to final, mass times acceleration dot dr. And what we know about acceleration is that it is the change in velocity, dv dt. And so this becomes integral from initial to final, m dv dt dot dr. And then you can do sort of a sleight of hand to say it's really a chain rule kind of argument here, but this can become then f dr dt dot dv. This becomes v, and so this becomes then integral mv dv. And so we get then that, because this is our velocity and this is a little differential of velocity, I've just changed my variables basically. And so then my mass, which is a constant, can pull out, and I just have this integral of v dv. And so the work is equal to mass integral from initial to final of v dv. This is again v to the first power, so we use our power rule, m v to the 1 plus 1, which is 2, over 2 evaluated from initial to final, which is just 1/2 mv final squared minus 1/2 mv initial squared, which is exactly the expression we had with our work kinetic energy theory. That is work total or work net is equal to kinetic energy final minus kinetic energy initial, where kinetic energy is given by 1/2 mv squared.